Thank you, Unity folks, for awesome WebGPU particle system content. And hello, everybody, and welcome. So we are here for the GDC 2024 WebGL and WebGPU Meetup. Thanks for coming. My name's Ken.
I'm Gregg.
We're going to be kicking you off today. Hi. Let's do some quick updates on the two specs. I'll start with WebGL real quick. So here's the agenda. What's going on first? WebGLs, we're still trying to transition it to more of a maintenance mode, but some late-breaking extensions are still going into the specification and the implementations to make your lives easier as developers for a long time to come. Mainly thanks to Alexey Knyazov, who's affiliated with Kronos, we've got a bunch new community-approved extensions, conservative depth testing, which speeds up some fragment shaders, no perspective interpolation, which is used by Skia and a bunch of other 2D libraries, blend function extension, which is, I don't know, it's been there for a long time, dual source blending. And since the release of Chromium 124, which is coming out soon, you've got the ability to render to RGB9 E5 textures, the ability to sample from stencil textures, and finally the ability to bounce your texture coordinates back and forth from 0 to 1. These are also in Safari Technology Preview 190, and that's coming out soon-ish, but Apple never talks about that. So anyway, thanks again to Alexey for this. The other major update is that we're still working on Engel's Metal backend, so we're trying to transition off OpenGL on Macs. Safari's already shipping this. There are significant bug fixes that, once again, Alexey contributed, and it's actually now passing the native DEQP for GLES 2 and 3 on Apple Silicon, which is an amazing achievement. You should look at some of the commits that he did, like transforming, I think, texture derivatives into the coordinate space of the polygon in order to get tests passing. It was insane. And there's also been a bunch of improvements to the runtime and the shader translator, thanks mainly to Kimo from Apple and Jeff from Google. Today, this is shipping in Apple Silicon. We were just about to ship it on Intel GPUs, but we had a little regression where we broke Flutter. That was like one small app. And then it turned out we broke Google Earth. And that's the point at which we reverted it. And then it turned out that we broke Zoom. And it was the intersection of this with a different feature called Out-of-Process Canvas Rasterization, or OOPC. But now I'm thinking of it more as oopsie. Anyway, if you want to hear all the details about that, find me afterward over a beer. So that is planning to go out once again in Chrome 124. And you will hear later from Chris and Luigi from Rive about an awesome new extension that he's been developing called Shader Pixel Local Storage. It lets you have persistent storage per pixel in your fragment shader. Thanks to Alexey for actually also helping fix a couple of key issues on Mac AMD and on Qualcomm. This is getting very close to a shippable state. And you can use it for a lot of cool stuff, as you will see in Rive's demo soon. And I think that's it. So Gregg, would you like to give a WebGPU update?
Sure. Right, so you've edited these slides, now I'm like lost. Right, so now, you all know WebGPU. Kind of think of it as a successor to WebGL, and it gives you compute shaders, right? And so it's still being worked on. We shipped it last May, and Safari and Firefox both have it under a flag, so coming soon. Hopefully by the end of the year, everybody will be, or maybe sooner, everybody will be in stable. And if you want to join, join. It's developed as a community thing. There are meetings that you can attend and give your input, or file issues on GitHub, and people will listen. Just if you're, calm voice and reasoned arguments. Yeah, so it's basically considered 1.0. There's been a few minor things that have happened, and a few things that get added at the last second since the other browsers haven't shipped yet. Like, can we sneak this other thing in and call that 1.0? Compatibility mode, which I think there's a slide on, I'll mention later, is coming soon. And new stuff has happened for, like it says, 8-bit.product and other things that are kind of, AI make AI go faster, which everybody seems to want right now. Also, pointers got relaxed recently, so that's a thing. I don't know if you're aware, but the spec is kind of split into brand new features and language features. And the language features, kind of like JavaScript, can just ship at any time. So the idea is hopefully that all the browsers will be up to date and those things will come in quickly. But you can check if they're actually there. Versus features of things like, can I make a texture that's enormous that some mobile machine might not support? So yeah, I mentioned this earlier, the implementation status, it's enabled in Safari Preview. Please test it. You can turn it on in Firefox Nightly, and several demos already work in both, and then there's some that don't. I'm sure there's lists of all the things that they're working on, but if you have something in particular you want them to concentrate on so that your thing runs sooner rather than later, they definitely look into that. Yeah. Compatibility mode has come up. So compatibility mode is taking WebGPU and running out on even older devices. In particular, OpenGL ES 3.1. So you can kind of consider this like WebGL 2 plus compute shaders. And the idea is that it's forward compatible. So if you write a compatibility mode WebGPU app, it will just run in any device that runs the full WebGPU. There's just some limits you have to meet. So like a couple of examples of lower limits is the minimum required number of compute shader invocations per work group in compatibility mode is 128, whereas in regular mode it's 256. So if you can write to that limit, then you can ship on compat. And there's a few others like color attachments. You only get 4 as a minimum. Now you could get more, but that's the minimum that is required to support that. So same with storage buffers per stage, you get 4. Another one that probably will only hit most people when you generate MIPS, and I have examples up, and when we get closer to shipping, we'll publish all that. But you need to tell the system whether you're going to use this texture for a 2D cube map or a 3D array, which is something you don't have to do in normal WebGPU. You can just declare it and use it any different way. So in compat mode, you have to tell it. Of course, in real mode, or whatever you want to call it, core mode, that information is ignored because the flexibility is there to do anything. But in compat, you need to tell it. And so that actually affects a few different things. The number one thing is when you generate MIPS, all the examples you've seen so far can ignore that. And in compat, they have to not ignore it. And so it just takes a few extra lines of code. I think I converted one. I think it added maybe 10 lines of code. And like, yeah, it's written here, the goal is to expand the reach of WebGPU. So there's a whole bunch of Android devices and maybe some Chrome OS devices that this will hit. The other one is Austin. Did he leave already? Austin wrote this awesome website, WebGPU samples. I think it was Austin, right, originally, and he wrote a whole bunch of samples of how to use WebGPU. And then they've been taking submissions to add some, and we just recently had a refactor to make it easier to take those submissions. So before it was like a React app, which meant you had to kind of integrate your submission into it. Now they can all run standalone, and they're just running iframes. And even you can take an external example. So if you have something that you'd like to show, we can just add a link and put it in the list, and it can show it directly from your site. There's 7 new samples that have been added into that repo. One for sign distance field text, skin meshes, a bunch of things. And you really come to the repo and add yours if you have something that you think fits. And ideally, it's something that you have code for, because we'd like people to go look at your sample and see how you made it. Yeah, so I think that's basically my part. WebGPU partnerships, all right. I think these are already shipping, are they not? There's a WebGPU versions of 3GS and Babylon.js. Maybe they're not at 1.0, but you can definitely ship them today. Also, all these other people are doing WebGPU stuff. Intel, TensorFlow, Google Meet is MediaPipe is Google Meet's MediaPipe backend, but it's available for other things.
Yeah, but the WebGPU backend is open source.
Not yet. Okay, well, we'll work on that. PlayCanvas also has had demos showing WebGPU stuff, and they're making progress on that as well. And Unity in particular, where is Brendan? Has been super contributing to all kinds of stuff, giving us feedback on what they need, and maybe he'll talk about it later. But he also has several tools, a parser that I've used for a bunch of stuff as well, and a debugger. I don't know if you're showing that tonight or not, but all of this stuff has really helped us move WebGPU forward. If you haven't done WebGPU, there's some articles up there that you could also contribute to. It's not. I'm trying to make sure it's not just me, even though I've written them so far. If you feel like putting an article up there, that would be great. And one of the good things about it is it's set up for localization. So if you put an article up there, there are volunteers that have localized some things into Japanese, Korean, Russian, Ukrainian, I don't know what else. And if anybody else knows when he wants to volunteer to translate those, it's set up that it's just really easy to start translating. And then Brandon also has all his best practice articles, which are amazing. And like he made one recently that shows off how to render a huge bunch of objects and like call them all in compute shaders. Maybe you're going to talk about that later. I don't know, but it's a really impressive demo on how to. Maybe it was a response to a comment I made when I first saw the API, and I'm like, "There's these render bundles, and like, what good are they? Because you have to like build them up front, put 10,000 objects in them." And I'm like, I don't always want to draw 10,000 objects. So I think Brandon took that as a challenge to be like, yes. He took it as a challenge. Say, this is how you do it. You can put all your objects in one giant bundle, and you can like use compute shaders to tell the system which ones to skip, and get a really fast result out of that. And so he has a demo up there that shows doing it all the different ways, one object at a time when you did it like without bundles and with bundles without the culling and with bundles with compute shader culling. And yeah, I don't even are you like doing per objects bounding spheres or box or?
I think in that example it's bound given.
Right. Another thing that shipped since last year at least is the timing API has been made public. So you can time your stuff on the GPU and find out how long the GPU stuff is taking. And so that's been hitting several of the demos now because you can put that in. Yeah, and there's all kinds of ways to contribute. Try the API, tell us what you don't like or what you think should be fixed. Of course, we ship 1.0, but we can add things. I know people are pushing for all kinds of different stuff, and right now I think the real core thing is try to get Safari and Firefox to hit 1.0. They're like, please don't add more to our plate. Until we ship, but we'll add them to the as soon as possible, ship us new things. There's conformance testing. I don't know if that's the biggest conformance tests out there, but some people complain there are more conformance tests for WebGPU than the whole of the rest of the web platform. We're trying to make sure that what you write is portable, and so we're working on getting those as. I think even with all the tests that are there, they're still less than 50%, or are they just over 50%? Right. So we're trying to like cover everything we can just to make sure we're all doing the same thing. And when you write something, it'll work everywhere. And of course, samples. Even if you don't integrate them with our sample list, I mean, tell us about them. We want to see them, and we can help publicize them. And yeah. Join the group, join the communities. There's a dev list, there's a Kronos list, there's a chat room, which I think is ridiculously busy nowadays, as I've heard. Twitter, Mastodon, all kinds of stuff. All right. Well.
All right, so Alexey Medvedev from Meta will present next on the state of glTF.
Yeah, hi, my name is Alexey Medvedev, I'm from Meta. Meantime, I'm a chair of 3D Formats Working Group. We kind of responsible for glTF and KTX and some other things. If you don't know what glTF is, it's probably most familiar to web file format. It's API agnostic, but it's designed to be super friendly to web. I hope you know what glTF is. I've not covered this, so feel free to reach me out if you want to know more details. I'm just mostly cover what's the latest for the glTF. So the previous year and this year, actually, we artified the forestation and extensions for PBR material. It's a specular anisotropy and then iridescence. Then we support WebP as the official texture format. We support GPU instancing and mashup compression. So we developed tools meantime. So we have a sample viewer official one. So that supports most of the glTF features. We have asset validator if you care about the consistency of your assets. We do support Blender. We support compression tools, etc., etc. And as for today, we have 4 tactical working groups: PBR, tooling, interactivity, and physics. And this is our roadmap. I will cover this a little bit later, but that's our kind of primary goals for this year. So we want to land physics, interactivity, external references. Again, I cover this. Procedural textures, it's kind of sort of MaterialX flavor for glTF, and some new PBR extensions. We released glTF on iOS. I know it's not web, but it's kind of big deal. Apple doesn't like us. We decided to go our way and implement this ourselves. Well, we kind of work around Apple a little bit. It kind of still, you can still use this full immersive mode. That means you can load glTF, place in your environment, play with this. Again, this is URL. If you want to download, please download, put 5 stars. As usual. So interactivity, and that's one of the biggest change for us. So glTF, it's a 3D format, but we are going slightly extend the meaning of the 3D asset. It's not just like a geometry, materials, and textures anymore. Actually, we think it's like the virtual object. And our sense, we want to improve, we want to add more properties into this one. And interactivity is just one of the properties. So that's kind of what if you want to load your glTF and do some kind of basic interaction with this, which is embedded into the asset. 3 main pillars here. We introduced glTF object model. It's literally you can address any property of the glTF by URI kind of level. So we have the specific extension for this. We call this animation pointer. It's literally like a pointer. You can read, write properties. We define the node graph-based flow graph. You may think this as events triggers, then flow and calculation, etc., etc. You can create your really complex behavior, but we do have some restrictions. Again, we keep in mind mostly web use cases. That means there is no dynamic instantiations, there is no lifetime kind of for the objects or sub-objects, etc. So we kind of, you preload everything, you know everything up front, you can sandbox it, you can control it though. And let me play this short video, how it looks like for today. Again, that's a completely altered in glTF behaviors. So you can run animations, you can trigger events, react on the events, etc., etc. The next big one is physics. glTF way, again, API agnostic. So we're not using any specific physics engine in mind. So technically we expect the properties of the collision shapes or rigid bodies can be applied for the most modern physics engines. So it's up to you how you implement the actual runtime for it. But it works as for today, for physics and other ones. We do have 3 implementations already. Blender support this, and then Babylon.js support this, and Godot support this. And we have validator support actually as well. And this video, that's exactly physics working. So all these balls actually, and all the interactions that happen in real time. If you open this QR code, you can play with this. And everything renders here by WebGL, by the way. Another major directions for us, it's a glTF and USD interoperability. We love USD, and we think we need to be friends and coexist. And for us, glTF is a last mile format. USD is the more like a outer-in format, and we're trying to find this kind of synergy between us. And perfect state, we want to do kind of lossless round trip between those 2 formats. And we working closely together with AO USD group, and we have perfect platform to do this. This is MSF 3D Asset Interoperability Group, thanks to Patrick. Yes, yeah, we have basically all the pieces to make it happen. And KTX, if you're not aware, it's super friendly again to web and any other GPU compressed texture format, which is not the final one. So the beauty of this format, it's almost ETC, almost PVR, almost ACTC, but we share most of the compression between all of them. And it requires additional small adjustment on the really last minute to be super friendly for your specific GPU. And super important, in my opinion, for web, because you deliver only one file, and then you can transcode to your final GPU in runtime in your player. What's next? First of all, we ISO standard already, but we want to work on the new submission this year. Most likely we'll include major amount of PBR ratified extensions and some additional ones. The list is in discussion. We're almost there. We definitely will release interactivity, external referencing, and physics. External referencing, it's a new file format. Actually, we call it glTF-X. And it's supposed to be a scene graph kind of approach. So instead of one single glTF file, we can combine many of them into this new file. And you will be able to reference this, add new extensions to be more cache friendly, or being able to replace some parts of the content, etc., etc. Again, this QR code, that's a working example of this complex scene and external reference thingy. So basically you see cubes and spheres. I know it's a kind of programmer art, but it demonstrates the idea that you can load multiple files and they're being referenced from the one single one. And also we want to roll out profiles, somehow similar to Vulkan, but serve our glTF needs. So basically just like specify the list of extensions that your players should be able to utilize. And the primary, at least for us, drivers nowadays, they're geospatial and commerce working groups. And this is a short video with the commerce beauty use cases that we have as for today. Everything here is web and glTF. And that's pretty much it. Thank you.
Thank you. All right, well, everybody get out there and start exporting your contents to the web via glTF. Okay, so next up, we'd like to welcome Brendan Duncan to the stage from Unity. And he's going to talk about a super exciting collaboration that's been ongoing for quite some time and some awesome new results.
Hi, my name is Brendan, and if I'm nervous, it's because they don't let me out of the basement too often, so it's nice to see you all in person. If I swear when I make a mistake, I'm sorry. You can bleep it out in the edit. So I'm a graphics developer at Unity. I focus on the web platform. So at Unity, we can build games from Unity and targeting the web. We use technologies like WebAssembly and all that. Historically, we've used WebGL, and a few years ago, as WebGPU has been in development, we knew that it was going to be a very important thing for the future of graphics for the web. So I took it on to start developing a driver for WebGPU at Unity. I did it because there's a saying, I do something not because it's easy, but because I think it'll be easy, and it ended up being the case. But worth it. So a quick overview of Unity's web player. So Unity is a big game engine. It targets a lot of different platforms, from desktop to mobile to consoles. And one of the platforms that it supports is the web. We think and truly feel at Unity that the web is a vital platform. There's a lot of benefits come out of it, freedom of, sharing your games and things with other people, the accessibility of it, a lot of benefits. So we put a lot of work into our web player, and some of the ways that it works is Unity engine itself is a very large C++ game engine. And then there's all the user land code, which is all in C#. And that's where people are making the logics and scripts for their games. And to get all that onto the web, we have all our C++ engine code, and then we have to take all the C# code, and we use an in-house tool that we have called IL2CPP, which takes C#.NET code and translate it to C++. And then we can bundle and put all that through WebAssembly compiler and scripting, come out with WebAssembly at the end of that, take all the JavaScript bindings, which integrate it into the web page, put that all together, and you have a game playing on the web. I glossed over a lot of details, but that's the gist of it. So for the graphics in Unity, because we support so many different platforms, there's a graphics abstraction layer called our graphics device, and we have a lot of different implementations: Vulkan, DirectX, OpenGL. We have a GLES OpenGL driver, and WebGL, goes along for the ride with that because it's essentially GLES 3.0 with some subtle differences, so we account for those differences. And then we take shader compilers, another big step of that. We have people authoring all their shaders in Unity, and typically HLSL, we have to get that to the end result that you're building, platform you're building your game for, or whatever you're building for. So in the case of WebGL, we take all the HLSL and we translate it to GLSL, and we use tools like HLSLCC, FXB, all that junk to get to GLSL. Results is you build your game, all the data's there, compiled, optimized for the web, it executes through WebAssembly, and you can play your game. It's kind of magical, but it works at all, but it does. So WebGPU is what I'm supposed to be talking about before I started rambling about WebGL. So WebGPU started being developed a few years ago, through the WebGPU spec committee, and we knew it was going to be an important thing. So I started writing the WebGPU driver, and long story short, we're shipping it as an experimental feature in 2023.3, but I'll get to that. But the fact is you can use it now. So how do we do with it? So WebGPU, a JavaScript API, web API. So we have to get that into our C++ engine. So there's ways of doing that in mscripting now. The Google people wrote the port of Dawn, exposing Dawn into, anyway. We wrote our own for a number of reasons, and it's open source, publicly available there. The reasons that we did it was that we wanted to optimize for WebAssembly usage. So we focused on things like garbage collecting and minimizing the communication from WebAssembly into JavaScript to try to optimize that as much as possible. Go follow that link, and our colleague Yuka wrote this library, and works really nicely. So we have that graphics device that we talked about, and so we take all the WebAssembly exposure, which is a set of header files, and then binding to JavaScript. But we can then write our graphics device against those headers and the APIs within there, and create the graphics device in Unity so that when it compiles to WebAssembly, it all just hooks up. So the graphics device does a lot of things. It calls into WebGPU to create buffers and textures and shaders and all that kind of stuff. But we also do a lot of stuff like caching, pipeline caching. You have all your state for what shader you're drawing with, the blend state and all that kind of stuff, and cache all that as a pipeline, and we can reuse pipelines, try to minimize creating objects and destroying objects, which is important for performance. And we do all the resource management, shaders and textures and buffers, so that we do that. The fun part is shader compiling. So shader compiling is much more complicated than with WebGL, because it's going to a new language, Wixel, which is a nice language. But we're still starting with HLSL, and we have a really fun shader compilation pipeline. So we go from HLSL as a start. We pipe that through FXC and HLSL CC, which generates, we have a custom version of that, by the way, which generates GLSL. We pipe that through GL Slang to produce SpearV, and then we pipe SpearV through Tint to produce Wixel. And somehow, I don't know how, but somehow, knock on wood, it works. Along the way, we have to do some massaging of things like in the GLSL, because we get tripped along the way. The Tint and Wixel do static analysis of shaders to make sure that they're valid. Sometimes it's hard to do static analysis. They'll produce false negatives. We massage the shader along the way to try to get past those obstacles. But we still have some obstacles to get past, but more or less it works. And we're improving. So like I said, it's available in 2023.3, which just got renamed to Unity 6. Same thing, different name. And currently it's an experimental feature. They don't like putting the word experimental on features, so we have it as a hidden feature currently, which I have a link at the last slide that points to a forum post that describes how to enable WebGPU for your project. It's really easy to do. It just takes an extra step. The nice thing about having with the WebGPU in there is that you can have multiple drivers that you're building your game or whatever for. So you can have WebGPU be the first one on there and WebGL be a follow-up, which means that if you're going on a browser that does not support WebGPU, it'll fall back to the next available driver, which will be WebGL. So you can design your game to run on multiple platforms, all the platforms it can. It'll always fall back to what it can, and then you can use things like feature detection to say, oh, my current platform doesn't support compute shaders, do something else, things like that. And then if you're on device that supports WebGPU, you'll get the compute shaders. If not, you'll get the whatever else. So what are some of the nice things that we can get out of WebGPU? And by the way, everything that I'm showing here is rendered with WebGPU on Unity. So you would get, what we want, compute shaders. That's the cool thing. So we can do things like GPU skinning, which is if you have skinned characters in your game, we can use the GPU to do that instead of the CPU. And you can get quite significant performance increase with that if you have skinned characters in your scene. We can do particle systems with VFX Graph, which was never available on WebGL because it makes heavy use of GPU-driven particle systems. And we can just do, whatever you want with compute shaders. You can write a compute shader in Unity, and it'll work. So you can do, marching cubes and ray tracing and all that fun stuff. So then we can do, there's other more advanced features in Unity, like forward plus rendering, which uses GPU to do light clustering and all these kind of fun stuff. And you can have unlimited lights per shader fragment, whatever. You can do other things that we do inside the engine that are more hidden from you, but you can benefit from, like pipeline caching. So if you play through your game, building pipelines, compiling shaders is the most expensive part, and that's true with Vulkan, DX12, whatever. So caching pipelines is a nice thing to do because as you play through, it has to compile a shader, build a pipeline, you'll get a hitch, move forward. But then this next time you play through, it's already been cached. It compiles all of those up front. You play through your game without any hitches. And we do a lot of stuff behind the scenes to make sure that you can have a smooth and performant experience using WebGPU. Some challenges. So this is a very negative slide, and it's no way a critique on WebGPU because there's reasons for all these things, but there are challenges that we have to overcome. So one of the challenges, limits. So WebGPU tends to have more restrictive limits than the other platforms, even WebGL. Things like number of textures bound to a shader or number of uniform buffers, or I don't know, all that kind of stuff. But it's more restrictive, and we hit those limits. And sometimes we can get around them by doing clever things, and sometimes it's harder to do. For an example, if you're doing a terrain system and you have layers of textures on your terrain, it's fairly easy to go past the number of textures for that can be bound to a shader, which happens to be 16. It seems like a lot, but combinations of textures makes it easy to go past that. It's just an obstacle. Another big one is the lack of synchronous readback for GPU buffers, which means that there's APIs which are not recommended to do in games, read pixels, read buffer, those types of functions because it causes GPU stalls and all that kind of stuff. But because they're easy to do, people do them all the time. And there is no equivalent of that in WebGPU. There's only asynchronous readback. We have an API for doing asynchronous readback in Unity, which makes use of the asynchronous readback of WebGPU. But the problem is that in the wild, you grab any Unity project off of GitHub, chances are there's going to be somebody doing a GL read texture or something, and it just causes problems. There may be solutions to all these things in the future, but can't promise on the future, just this is the state of now. Validation errors, similar to limits. WebGPU is strict, and rightfully so, because you don't want malicious actors attacking your computer on the web, but it makes doing the fun stuff harder sometimes. Hackers ruin everything for us. The texture format limits, sometimes formats have more restrictions than other APIs, typically because they're like an extension of Vulkan or something, and extensions aren't exposed by the base feature set, so they will come in the future as extensions for WebGPU, but we hit a number of those just by taking existing content. And there's missing features of WebGPU, like textile buffers and things like that, which will just come in the future, but again, talking about existing content. And then uniformity analysis has been the bane of my existence since it came about. I understand its requirement and need. You know, hackers, again, ruin everything. But the problem is that it's a static analysis of a shader, and it produces a lot of false negatives, and sometimes they're more challenging to work around than others. And this is typically for compute shaders, and it's very not hard to write a compute shader that will break the static analysis of uniformity analysis, which means as you compile it to WebGPU, it'll yell at you and say, no, you can't do that. And you say, why not? I'm not doing anything wrong. Stop yelling at me. And it says, no, don't do that. That's just we're figuring out solutions to all these problems. So then Unity is a massive engine. It's a very complicated engine with a lot of flexibility. It's very hard to test. So one of the things that I found difficult to do was debugging. So there wasn't really any existing debugging tools for WebGPU. Okay, it's brand new, so give it a break on that. But it made developing something on an engine as large as Unity quite difficult. So one of the things that we did was we can build for the native Windows or Mac or whatever player game and use the Dawn library, which is the C++ implementation of WebGPU, and then we can use Visual Studio and RenderDoc and all those fun toys. But it's not truly representative of the build for the web, and there wasn't really anything equivalent for the web, so I took it on myself as a hack project to create a new debugger, which has been quite useful for developing for Unity because I did it on the side. I made it open source. You're all welcome to use it too. So basically, it's a Chrome extension, took inspiration for awesome projects like Spectre.js and those type of things, also from RenderDoc. And so you can do things like frame captures, where you can capture all the commands that go into rendering a frame, look at each command, all the arguments that go into it, that command, and also all the state that goes into it, the textures, the buffers, the uniform buffers, the storage buffers, all that kind of stuff, and look at their content. So I use that for, like, I'll take a Unity project that's misbehaving on WebGPU. I'll make a Vulkan build on Windows. I'll run that through RenderDoc, do a frame grab there. I'll do a frame grab from WebGPU using my inspector tool. And then I'll just step through the commands one by one, and I'll look at the buffers and like, oh, now here's one that's different. That doesn't look right. And I can use it to narrow down what the problem is by looking at a working example versus something I messed up in our WebGPU driver or something like that. So I fixed a number of bugs using this tool. And you can do things like also record all the data and commands that go into the render, like the capture, but then it'll create a self-contained HTML JavaScript, which then you can use to send a self-contained isolated bug report that is just the render minus any of engine stuff. So then people like you guys at Google can take that, and you don't have to unravel a full executable WASM thing. You can just get JavaScript. Again, here's the link. And it's also on the Chrome store. I'm actively working on it, so welcome to add any suggestions. And again, here's the link that we have to our forum post where we give full information about how to enable WebGPU for Unity, and you can also ask any questions about it, and I'm always on there answering questions as I can, and I answer questions when I can't either. Sometimes I just make stuff up, but you'll never notice the difference. That's it for me.
I just want to say what an awesome collaboration this has been over many, many years, but especially over the past like 3-ish as we've been working on the WebGPU backend for Unity together. And so given that we're at the Game Developers Conference, you know, probably many or most of you are making games, and this is a great way to get your content onto the web with like almost full fidelity compared to the native version. So we're very, very excited about it. By the way, all the slides will be posted after this, so please don't hustle to take pictures of slides while they're up there. Right? Right? We will post these later. Yeah. Yeah. Posting slide. Okay. We'll post all the slides, so please don't worry about taking quick pictures. So next up, we have an awesome integration story into Unity, as a matter of fact, from our friends at Rive. So please welcome Chris and Luigi to the stage, and let's hear about some awesome vector, curve, and path and animation rendering.
Hey everybody, I am Chris Dalton from Rive. If you remember last year we came and talked about a render we've been writing. We've been adding an extension to Chrome for WebGL called Pixel Local Storage that is now being added in WebGPU, and we'll have that soon hopefully in WebGPU, and WebGL it will be released soon. We demoed a renderer using Pixel Local Storage, and it was closed source, so we just kind of demoed it. And as of this week, a couple days ago, the Rive render is open source. It's ported to WebGL 2, uses Pixel Local Storage, and so we're just going to give a brief overview of kind of what we're doing to render vector graphics. And a quick intro to Rive. Rive is a motion graphics vector animation tool for creating UIs and things like that. So the renderer we have built that runs on top of WebGL 2 with the extension, and the Pixel Local Storage extension is in draft form. If you enable draft extensions in Chrome today, you can use it. The way it works is here I have a path that we're drawing. The one in the middle is not anti-aliased. Our approach is actually really quite simple. We make a stroke called an anti-aliasing stroke, for lack of a better word, and this renders coverage into Pixel Local Storage. Coverage is a fraction, 0 to 1, says how much coverage does the pixel have, and then you blend it into the frame buffer based on coverage. So all we do is we stroke the path with this coverage. The stroke here is, on the right side is orange, which means negative. On the left side is blue, which means positive. So right down the middle on the left side, we taper from 1/2 coverage to 0. On the inside, we taper from -1/2 to 0. If we draw that on top of this heart, we end up with a little anti-alias thing. If I bring this down to 1 pixel wide, here's what you get. If you draw this anti-aliasing stroke 1 pixel wide, then it looks like that. Again, the blue are positive, orange is negative. Those get drawn on top of this, and it gives you an anti-alias path. It's super fast. The triangles we emit are here. We do the tessellation. We actually do the tessellation in WebGL 3. And the way we do it is we render vertices to a data texture. And it works, it's fine. But we don't have tessellation, we don't have compute, but we render a data texture to do the tessellation. The triangles for the anti-aliasing stroke are, So basically what you do is when you're drawing the stroke, we segment the curve up into points, and at each point you imagine a bounding box the size of 1 pixel, and you outset to one of the corners of the bounding box, the one that your normal points to. In other words, the sign of your normal is your outset, which is why around here you get these cool artifacts. And yeah, so basically this is how we're rendering. We do this stroke, and we accumulate all these values into Pixel Local Storage. And as we draw every single pixel, we just blend into the frame buffer as we go. So when you get a double hit, like if this pixel here gets hit twice on the second hit, we know what coverage was last time it got blended, we know what coverage is now, and we can kind of figure out how to blend it in to make the final correct color. So no double pass rendering, we just draw these triangles and the path is done. And we can batch all of these together. The other cool thing about this is that this anti-aliasing stroke is a stroke. So if a path is stroked, we can actually use this geometry as a stroke and draw a stroke. And if it's filled, we can do this thing. So what we end up getting is we tessellate all of our vertices, and then in many instances, we issue one called a GL draw elements indexed instanced, and the whole screen fills up with our paths. Yeah, so I mean, just quick review, and we can talk about this later, but simple stuff. Fractional coverage for anti-aliasing is interpolated across triangles we accumulated in pixel local storage. One other note here is, and this is more implementation detail, we emit these in such a way that the negative ones are counterclockwise, positive ones are clockwise. So if a triangle is counterclockwise, it gets negative coverage, clockwise it gets positive. So again, it's a nice way to just generate these triangles and blast it out. We can do it all in a single pass, batch everything together. The tessellation happens on the GPU. So I will give a demo. Here is our Rive renderer running in WebGL 2. And using the pixel local storage extension, drawing a path, draw something kind of more interesting. Here's a fun scene. Okay, yeah, we're limited to 60 frames a second, so it's moving slow. But we have a whole bunch of different blend modes. Again, we can do the blend modes in pixel local storage. This green light is one of the SVG blend modes. The lights change colors. Every single thing here is a path rendered from Bezier curves every frame. So you can have the infinite resolution on all the paths. All these windows are all stroked out here, every single one of them. The anti-aliasing is very, very crisp. And, I mean, we can draw another one, and draw another one, and draw another one, draw another one, draw another one. I mean, we're still just 60 frames a second drawing all these things. It's just really simple. We just get a bunch of triangles, ship them off to the GPU, and then it just goes. Here's another one, an example drawing text. Again, you can see the quality of the anti-aliasing here. It's really, really high quality on all the layers. You get on these, we can fill in more letters, more. Now we're starting to drop below 60. And that's WASM. That's WASM, because for every single one of these letters, they're composed of Bezier curves. And what the WASM does is we do package up these Bezier curves. We put just the curves, the control points of the curves, in a buffer, ship them off to the GPU. But doing that takes a little bit of time, especially on WASM. And I want to show one thing, Chrome flags, draft extensions. This is where we're getting the pixel local storage extension. If I disable it, oh, relaunch. There it is. We're falling back on multi-sampling. And you can see a big difference in the quality of the glyphs. And this actually looks like it's, I have to look into that. It looks like 2 samples, not, yeah. This looks, yeah. Well, at least it's not 1. Anyway, so when you don't have the extension, we fall back, we use MSAA. And you can see the difference in quality. I'll turn on the pixel local storage again. No. Cool. And now Luigi is going to demo our WebGL integration into Unity.
Yeah, so the reason why we care about a renderer that can do this every frame and repackage those curves every frame is because our tool lets you change those curves every frame. And particularly when you're making user interfaces and motion graphics, you really care about being able to change the data every single frame. And if you want to, if you don't need to, you don't need to. But we wanted to make sure that we have a graphics renderer that really allows you to do that if you want to and make that the baseline. So here's a simple example. Just recently, we've been adding support to Unity. The way we do it is we use the native plugin system, and we're actually going to try to talk to Mr. Unity later about how that's going to work with WebGPU. But as an example, you drag in a Rive file. A Rive file is just something that our editor spits out that uses a custom format that we built that knows how to use our renderer really well. And if I drag a file in, yeah, I can show the editor later, but if I drag a file in, you can see it's already animating. Here I've just added it to the camera, so it actually draws on the screen, but I've also mapped it to a cube, and if I hit play, you'll see that in Unity it works. It's interactive. I can click on it, and it does stuff. And as of this week, we've also got it working in WebGL, so using the native plugin interface. Yeah, we took all the work that we did with PLS specifically, and it now just works with Unity. There's a few tricks because Unity tries to massage your shaders, and we have to convince Unity to not massage our shaders, but it's actually Mscripten that tries to massage the shaders for some uniform bindings and things. But give it a sec to build, and I'll show you that this works with the same fidelity as it does in Unity Native. And then I'll show you a slightly cooler example with more animated stuff. But yeah, the whole point of Rive is that you draw your vector graphics in a tool that is artist-friendly, and then you can just export that work into any game engine. Unity is the first one that we integrated with, but we have support for Unreal, we have support for custom engines. The whole C++ runtime is open source, and as of yesterday, the runtime is open source too. And you can see that this it just works. I'll show you a slightly more fun example. This is just a basic one, but this is one that builds out some kind of cooler scenes. I'll build it for web. And you'll see that we built out a fun menu. I'll go full screen, but unfortunately I have to hit escape and it keeps popping out of full screen. But this interface is built in Rive, and so this is all the PLS renderer doing all these scenes. But then if I click on one of these, like this one, you'll see that yeah, all of this is dynamic, so I can make it switch colors. I can animate the text. Everything is redrawn every frame. The text is also redrawn every frame. There's nothing cached here. That's one of the things that was really important with this renderer that we couldn't get with other vector graphics renderers, was the ability to actually do this completely dynamically every frame. This is going to jump out, which makes for some really fun animations for build things, for projections like this, for text. We can rely, because text and everything isn't a special case, we can let the artist kind of go crazy and create everything and not have any special restrictions. Text isn't drawn in a special way. We don't have a special path for text. Text is just more, it's just more vector graphics, and because of the fantastic anti-aliasing we have, it just works, and it looks good. Let me see another. This is kind of a fun one where we've actually mapped it to a 3D mesh. We've mapped the Rive animation to a 3D mesh, and you can change its expressions and things. And you get all the fun things with interactivity that was mentioned, similar to glTF. You get events, you can pipe inputs to the state machine, and the cool thing is that the artist is in full control of this, and they can bring it to any platform, and it just works. I have plenty more demos, but yeah, you can use it for user interface design. You can use it for cool things projected in 3D, menus projected in 3D, which is particularly fun with Unity, if I can remember my shortcuts. Yeah, and yeah, we do this by bringing each backend individually. We have an OpenGL backend, which we've got working on the web. And like Chris said, we have a fallback for MSA. So today, if you don't have PLS, we will fall back to MSA. This is using PLS right now, so it looks particularly good. But yeah, we're excited to make this broadly available, and we're excited to see what other people will do with the renderer as well. Cool, that's it.
Awesome. Thank you both. This is a huge step forward for the community, so thanks for integrating with major game engines and getting this out there. So next, please welcome Henrik and Ashwin and Nicolas from Autodesk to the stage. And they're going to talk about the current state of USD and MaterialX on the web. I'm excited to know what it is.
All right, so let's get started. Yeah, so we're all from Autodesk. So we already heard a little bit earlier about glTF and USD and how they relate to each other. So, you know, a lot of us are coming from a web background, so I'm sure many of us are familiar with glTF, and we're all active in the glTF development as well. But USD and MaterialX comes from another perspective. It's more about the authoring aspects of your workflow, whereas glTF is more focused on delivery, being very efficient for transmission. And while there is support for animations and now physics and interactivity, it's still more of a baked version of the of your asset or your scene data. Whereas in the case for USD, it's more designed for the authoring or content creation stage of a project. So it's more the source of truth data where you can edit everything, and you often have many teams or users working together on a project that could run for years potentially if it's a complex film production. In the case of USD being used in film, but also same for games, or now growing into other areas that like AC and manufacturing type of projects. So as we go through USD and MaterialX, just keep in mind that glTF and USD are complementary. They are targeting different aspects of 3D assets and scenes. So what is USD, or OpenUSD as it's now branded? It's an open source project from Pixar that they open sourced in 2016. It's not really a file format. Well, it certainly describes a scene graph, but it's more a software platform. So a high performance extensible software platform for collaboration workflows of large 3D scenes. And USD is interesting in several different ways. It does have a lot of built-in constructs for facilitating collaboration, like the composition engine, layers, variants, and this concept of non-destructive override. So you can have many people working on the same project at the same time without interfering with each other. It's also very extensible in several different ways with asset resolutions, file format, and custom schemas to basically extend it with any sort of property that you might need. And then, since we're talking about WebGL and WebGPU here, the rendering aspect, we have something called Hydra, which is a rendering abstraction framework, which is particularly interesting to us at Autodesk, and we're investing heavily in that part of USD. But it's really a way to separate how you describe scene data from how you render the scene data, so you can get more flexibility in using different renderers for your application. So yeah, and both USD and MaterialX that we'll hear more about in just a minute, they come from historically a desktop background. So not really being designed with web in mind from the get-go. So a few years ago, we started looking at bringing USD and Hydra to the web. So we added WASM support and open sourced that in late 2021 with some JavaScript bindings for both the USD and Hydra APIs. So you can run the whole software stack basically in your browser. We also open sourced a very simple render delegate, just so you can see your scene in the browser, which was based on 3GS. All the latest work is going on in the branch that I'll link to here, and there is also a growing community around this. So there is, on the Academy Software Foundation, there is a working group looking at USD on the web, and getting more and more people participating there and building on what we open sourced here originally. So if you're interested, please join the Slack channel there, and you'll get connected to many more people that are working on this. So I'll go back to the rendering aspects here of USD. So Hydra again has the separation of how you describe the scene from how you render the scene. So your web application can describe your scene data. It could obviously be USD scene data, but it might just as well be a glTF scene data or any sort of custom scene data, your native scene graph that you have inside your application, or any sort of file format you want to support, and you can combine all these different streams together in the same scene. So mixing your custom scene data with USD scene data and multiple different other file formats. And then you have several options in how you render this. And there, of course, there are many options available in a desktop environment or mobile for that matter as well. Like Apple has put a lot of effort into USD, and you see support for USD and Hydra in both Mac OS and iOS, and now the Vision OS. But for the web, we basically have 3 options. So we have the Storm render, which is the default rasterizer that comes with a USD library. Then we have the JavaScript render delegate that we released originally there for 3GS, or based on 3GS, I should say. But you can add any sort of render delegate of your own, whether it's a JavaScript-based one or a native engine that you cross-compile. So all of these are interesting depending on your workflow. You might choose one or the other. We from Autodesk are primarily looking at Storm because we do see a need for having consistency between like our native, or maybe even the same application running in a native environment on a mobile device and in the browser. And Storm has this abstraction layer HDI that can target all the different APIs. So we're able to run this exact same renderer on the desktop, on Android, on iOS, and also now in the browser. But depending on your use case, that may or may not be the renderer choice for you. So we did have a presentation on this in the meetup in July. We went a little bit more in depth in how we added WebGPU to Storm. Ora Munoz on our team went into more detail, and a lot of the similar challenges and experiences that, like we heard from Unity earlier, pretty tricky shading pipeline and whatnot. But yeah, it's been very successful so far. Some of the recent features we've added since the last meetup, text rendering, billboarding, multiple viewports like you see here, IBL and various different shader effects. And yeah, we have more work in progress there on ambient occlusion and running PDFs and whatnot. So that's some of the work that we've done on the Autodesk side, but there's been plenty of other community projects as well. So these are just 2 examples. So Needle Tools, they built off of the original work that we open sourced with a full assembly of USD. But then they also extended the 3GS-based render delegate to be more capable and supporting a lot more features. We have Cloud Zeta, which also has kind of a full USD stack running in the cloud and in the browser. They have their own render delegate based on the Diligent engine. So that one supports WebGL through WebAssembly also. So those are just some examples in how you can kind of use USD in a browser environment. All right, so that was it from the USD side. I'll hand over to Ashwin to go into MaterialX.
All right, so MaterialX is another open source project, part of ASWF. It's an open standard to represent materials for interop. So it doesn't dictate material transport. The way it does it is by defining a specification of nodes and the interface for those nodes. So you put together these nodes as basic building blocks to describe your materials. And using those, you can describe glTF PBR materials, standard surface, and the open PBR material that Nick will talk about. MaterialX is currently 138.9, and we have C++, Python, and JavaScript bindings. And one of the components in MaterialX is the ability to generate shaders from these node graphs. And it can currently generate GLSL Vulkan, Metal, and open shading language shaders, and even NVIDIA MDL shaders. There is new work that's getting added to add non-photorealistic rendering, NPR, so it can also do those kind of nodes effects. So over the years, MaterialX has gained a lot of industry adoption. So by default, it comes with its own viewer and a graph editor that folks can use to author materials and share them along. But over the years, there have been participation from Apple, Autodesk, Chaos Groups, NVIDIA Omniverse, and Pixar, and many other render engines. So just like Henrik said, these MaterialX was more targeted for production, movie, and desktop pipelines. And we took on this effort to bring it to the web. So we started doing same as what others have done, WASM bindings, creating JavaScript layers for it, and trying to generate GLSL, ES shaders and all that. So this was open sourced 2021-ish, and then we've got a lot of contributions from the community to extend it further. So what's open source? What's available on the MaterialX web platform is the core layer, which is responsible for parsing the MaterialX data, and gives you the basic types. There is the shader generator that's also available, but that's optional. So you are not required to use the shader generator. So for example, 3JS, it uses MaterialX, but it has its own shader generation. There is also a web viewer that that's available out of the box. So here is a demo. I mean, this is what is available right now in MaterialX GitHub repository. It has a viewer that's using 3JS. It uses the 3JS glTF loader to load this scene, and it generates the GLSL ES shader from MaterialX graphs, and then sends them to 3JS raw shader material. So it's using 3JS as a renderer, but it's pretty fluid. No WebGPU yet, looking for contributions. And what we have so far is things like where you can drag and drop stuff, frame captures, property editing, and support like half-float HDRs, which are really required for web workflows. AMD picked up this viewer and has integrated that into their GPU open platform. Check that out. Very pretty samples. Nice, fun thing to take a look at. MaterialX with glTF. So this was a call to action from the Metaverse Foundation, Metaverse Forum, where besides material descriptions, there's a common workflow where folks use MaterialX to describe procedural patterns. So like things like marble texture, or something like taking a procedural brick patterns and things like that. And transporting this across renderers is a pain. You have to bake it down, and you cannot do variations. And this is something that so the call to action was, how can we make this better? And the Kronos group took on this challenge to create a subgroup under 3D formats PBR task group to focus specifically for procedural material interop. And that's what Alexey was talking about, the glTF procedural texturing initiative. So we meet bi-weekly, that's every 2 weeks, Tuesdays, 9 p.m. PST. Would love to have your participation. So I chair that group. We have a liaison, because this is an ASWF project. So we have Bernard Kwok, who's our liaison between ASWF and Kronos, and making sure both of these groups can work together. Ed McKay is still our PBR TSD chair. So this is a rough layout of how we are looking at building this KHR texture procedural extension. So the workflow would be, you would continue to author your material patterns using MaterialX node graphs, and you would, and the extension describes the JSON specification for describing glTF procedurals, and then there will be tooling to convert that MaterialX graphs to the KHR procedural texture extension, and you'll be able to still bind that into your existing PBR metallic roughness extensions. So instead of providing a texture, you would provide a procedural graph. And the tooling would help you process these graphs and generate final image or bake that down, things like that. Now I'll hand it off to Nick to talk about OpenPBR.
Hi, I'll just give a quick update about OpenPBR, the material model that's now public and under the Academy Software Foundation Basically, this came about with an announcement last year, and Autodesk and Adobe collaborated to pretty much combine these two material models, so the Autodesk standard surface and Adobe standard material, and this new open PBR surface borrows from both of those and has many commonalities, while a few key differences, such as the fuzz layer that's replacing sheen, you'll see on the top there. Both of these models are widely adopted, so that was a good basis to start off this effort. So as I just mentioned, this is public and under the Academy. There is formalism in the white paper that we're linking to below, and this slab model, and it's basically a mixture of this kind of like layered closures that you can use to build up a physical material model. Now, the important bit here, I'll refer you to the white paper for any details in the parameterization and the specification. But the important detail here is we do have reference implementation in MaterialX already, and a few products have already even natively implemented references. So, as was mentioned earlier, and I just said, there is a MaterialX reference. You can go right now to the link below. There's a node graph and node depth there, and you can shader gen to targets, like basically if you want to just go and use the MaterialX web viewer there and try it out live. There is also another reference, which is WebGL path tracer. We can see on the right the kind of results you can achieve, and I would encourage you to go and try this out as well. I have a short recording of this. You can see here in action. So linking for the web, loading there, and playing around with some of these parameters interactively. All right, so in conclusion, this is under an open standard under MaterialX and the Academy at the moment. Version 0.3 was just released as a preview, and we'll link it here. We are targeting to have production 1.0 version by SIGGRAPH this summer, and any involvement and feedback is welcome. There was also a recent AO-USD announcement where it was mentioned that this is already implemented in Omniverse, and OpenUSD will adopt this as one of the main material models. Please join us in the technical steering committee and give us your input. Okay, that's all from me.
Super exciting to see these filmic technologies coming to the web. For our last presentation tonight, please welcome Brandon Jones from Google, and he'll be talking about how he principally brought WebGPU to these little devices here.
All right, sorry about that. And I apologize, I've been talking to a lot of you lovely people, and my voice feels like it's going out a little bit. So if I feel a little bit froggy, I apologize for that. So yes, as Ken mentioned, my name is Brandon Jones. I'm a software engineer on the Google Chrome team, working on WebGPU, and today we're going to be talking about shipping WebGPU on Android, because that's what the slide said. So as you're probably aware, WebGPU is now shipping on Android today. As was pointed out earlier, it's also shipping on Chrome, has been for a little while. It's only been shipping on Android since January of this year. And it's shipping on a subset of Android devices. So at the moment, we're targeting anything with Android 12 and up with either a Qualcomm or an ARM GPU. And we figure that that covers probably about 50% of the Android ecosystem. We do want to extend it out to more devices later. And because this is a graphics talk, we have to have some pretty pixels. So we're going to check out a quick demo from PlayCanvas, who was actually supposed to be here tonight, and unfortunately wasn't able to make it, but I will show their stuff off for them because it's really cool. So the fun part about WebGPU is you can probably go to that URL right now, and there's a very good likelihood that the device in your pocket will be able to run it, unless it's an iPhone, and I hear the EU is working on that. Sorry, Ada. So this is from, like I said, a company called PlayCanvas. They've had a WebGL engine for a little while. It's a very nice one. And they've been doing work to port it over to WebGPU. This is one of the first demos that they put out to show that off, mostly demonstrating area lights. Now what you can see here is from left to right. This is running on a Pixel 4, a Pixel 6, a Pixel 7, a Pixel 8. I've never seen a Pixel 5. I don't think they exist. But you've got 4 different generations of devices here that it's running on. And it's running quite nicely on all of them. But of course, we have a bunch of pixels around the office at Google, but we have tested this on a variety of other devices as well to give us confidence that we could actually ship. So because we're talking about Android, we're going to be talking about Vulkan, because that's the modern GPU API for Vulkan, and that's what Chrome's WebGPU implementation called Dawn uses. We use it for both Android and Chrome OS right now. We will eventually use it for Linux, but there's some other dependencies that we need to resolve before we can get to that. And we have a pretty small list of Vulkan requirements that we require before we can use it as a WebGPU implementation. They're all right there. And this was very specifically chosen to not exclude too many devices. And a happy side effect of that is because we were so careful about making sure that we didn't exclude anything, we can actually run this same demo all the way back to a Pixel 1. We are not shipping this right now because there are other graphics bugs there, but it does technically work. And I think that's as far back as you can go before, if you get too much older than that, then the Vulkan versions just aren't new enough. They don't have the right features. But we feel pretty good about the potential reach of WebGPU as a result of this. Now, I didn't work on the core Vulkan backend. That was the work of my teammates such as Corentin Welez and David Neto. But I talked to them about their experience implementing on Vulkan, and some of the highlights that they wanted to point out about this process was that we found the Vulkan spec to be extremely detailed, which was very, very helpful when we were building an API on top of it. There was a lot of scenarios where when working with the other APIs, we would actually have to go out to members of those companies and say, okay, what is exactly the behavior that you're seeing here? And in Vulkan, that rarely happened because the spec was so detailed. Additionally, they are very precise about things like memory access and floating point behavior and whatnot. That's both helpful to us as an implementer and inspired us to be more precise in our own specs. The Vulkan validation layers were very valuable on the devices that we were implementing it on. They work, they catch a lot of bugs. Highly encouraged that anybody working with Vulkan should use them. And we found that working with the Vulkan group at Kronos was extremely productive. They were very helpful, very quick to turn around on bugs that we brought about the spec or undefined behavior or anything like that. It was a really good partnership, even though WebGPU is technically being developed under a different standards body. There's no animus there. We all get along great, as evidenced by this meetup. So the biggest challenges that came with using Vulkan for a backend is just simply that WebGPU is an API. It's not an app, it's not a game, it's not an engine. And so we need to ensure that every corner case of every code path that we expose can reasonably be expected to work. We can't just say, oh, we'll take that particle effect out because it doesn't run well on this device. It's not really an option for us. And as a result, we tend to see all of the driver bugs. And also, while it's not really unique to WebGPU, Vulkan is very much a bring your own utils API, and so we had to bring our own utils like everybody else, reinvent a lot of wheels for things like allocators, pools, caches, whatnot. It's not unexpected, but it is something that adds to the complexity of the Vulkan backend versus some of the other ones that we implement. And that complexity tends to lead to Vulkan's reputation as being a little bit verbose. You can see here, this is an image that somebody else put together showing how many lines it takes to do a hello world in each of the APIs. So you got DirectX down there, OpenGL up there, and then Vulkan up top, which is the longest one by a fair margin. And that complexity holds true for Dawn as well. We find that the Vulkan API is our largest by far. It's more than twice the size of our Metal backend. And it's worth noting that these numbers are actually a little bit smaller than you might expect normally because we have an awful lot of logic that was pushed to a common front end that's platform agnostic. So with that in mind, let's talk about shipping on Androids specifically, which is the part that I was principally responsible for. At the point that we started working on the Android implementation, we had already shipped Vulkan on Chrome OS, and so we knew that our foundation was good. And it really broke down to a question of how well does that scale to the much larger ecosystem and much more variable quality ecosystem of Android devices. And the pleasant surprise was that generally it just worked. I mean it very literally when I say from the very first moment we got WebGPU pixels up on Android, I could probably render about half of the sites that I knew of at that point. It's a real testament to both the portability of the Vulkan API and to the quality of the code that our team implemented, that so much of it just worked right out the gate. The things that didn't work were usually platform-specific, like cross-platform shenanigans or driver bugs. Now, when it came to hunting down those driver bugs, probably the #1 tool in our tool belt was the fact that we have a very robust CTS. I believe this was mentioned earlier, how ridiculously large our CTS is. But this was great, because what would happen is I would get a new device, plug it in, point the CTS at it, wait hours, it took a long time, but then come out the other side with a very direct list of these are the things that are a problem on this platform. And that allowed us to focus our efforts quite a bit more. Our reliance on CTS is a lesson that we learned from WebGL, where its own CTS has proven invaluable in keeping it running over a decade or more of use on the web. So an example of the type of thing that we saw on a platform level, something that was unique to Android, is that WebGPU guarantees that you can use either RGB or RGBA or BGRA textures when you're rendering to a canvas. But on Android, because of the cross-platform architecture that Chrome uses, we have to shuffle everything through an A hardware buffer, and A hardware buffers only recognize RGB textures. So in order to enable this kind of flexibility that the spec guarantees, we just had to do some fix-ups where we did a last-second just-in-time copy from the wrong format to the right format. There is some overhead to that, but we knew about this when we were going into it with the spec, and we've built in a method where you can actually query and say, hey, what's the right texture format for this platform if I want to avoid this overhead? So it's not unexpected, but it is something that was a unique problem on Android that we had to work around, and that probably accounted for a good 25% of the rest of the things that didn't work after initially getting things up. When talking about driver bugs, we found some fun ones, and so I wanted to talk about a couple of specific examples. We saw one vendor where we were getting a device loss anytime a texture was modified in a compute shader, and then immediately turned around and rendered in, used in a render pass. But only if they were part of the same VK command buffer. Now, this is the type of thing that you'd say, well, surely we did something wrong with the barriers. We could not find, or I could not find, anything that was going wrong there. But in order to work around this, we took advantage of a feature in Dawn where when you are generating command buffers with WebGPU, those JavaScript calls do not immediately go down and make an equivalent Vulkan call. Instead, because of the cross-platform architecture that we're dealing with, we built out an intermediate version of that command buffer and only toss it over the process barrier when we're ready to submit those commands, at which point we build the actual Vulkan command buffer just in time and send it off to the GPU. This means, though, that we knew the entire scope of the commands that were going to be submitted as part of that buffer. And so we could look for this specific scenario and say, hey, we recognize that we use or modified the texture here, use it here, that's not going to be okay, and we would split the command buffer between those two passes. So we record everything up to that point, split it, record the rest, push both of them as a single commit. It allowed us to work around this class of problems really effectively, and is completely invisible to the user, which is great. We encountered similar issues on the shader side, where we would run into things like on a different vendor, if you tried to pass a matrix as a function argument, you just crash. I don't know about you, that seems like a common thing to do, but hey, didn't work on this particular set of drivers. Now here, we were able to really rely on the fact that we have our own shading language. We have WGL. Rather than consuming something like SpearV directly, because that meant that we have to have a cross-compile step, and this issue could be worked around during that cross-compile. In this case, we just simply said, well, anytime we're passing a matrix into a function, pass a pointer to the matrix instead, and fix it up for me. This kind of fix-up would have been much more difficult to do if we had been consuming a bytecode directly. Whereas because we were already doing this translation, it gave us a really clean point to do this sort of just-in-time correction. Now, we try to address every bug that comes along, but occasionally there's ones that are just impractical to work around. And an example of this is that we found on some devices, if you tried to pass an index that was like the maximum int and render a non-list topology, which meant that there was no primitive restart value in play, again, you would just crash. You'd get a device loss. And it's really annoying, but there's not a practical way for us to detect this without just destroying performance. The only way we can reasonably do it is looking through every index that you were about to submit in every buffer and say, is it the magic value? No, we're not going to do that. And so in a case like this, we're able to look at it and say, well, this is clearly a developer mistake because, especially on the devices in question, you simply cannot have buffers that large that this is going to be a valid index. And it's easy enough to fix, just don't give us that index anymore. And while a device loss is really annoying, it's not actually dangerous. It's kind of like the driver's immune system saying, nope, that's not great, and shutting down, which is exactly what we want because it means you didn't leak anything. We didn't expose any dangerous data. We didn't have any undefined behavior. We just died. So this is an example of an issue where we say, this is okay. It's an issue, it's a driver bug, we know about it, we talked to the company about it, but it's not actually going to block us from running, and it's far preferable to leave random edge cases like this in that are probably not going to be hit by most people than blocklisting an entire device because of something that most people will never hit.
Was that found as positive?
No, that was just found with the CTS. Because we have a lot of CTS tests if we have not made that point clear. Now, that said, talking about block lists, we do have a block list in case we need to use it. I don't think we've actually blocklisted any devices specifically yet, but we have found that sadly sometimes the block list just isn't enough, because we have found at least one very old GPU where simply asking it, "Can you Vulkan?" makes it break down and cry. And by this I mean, if you call VK enumerate physical devices, the very first Vulkan call that you make, the device crashes, which is not great. And this is problematic because our block list actually relies on information returned by that call in order to determine whether or not you should be blocked from making further calls. So we have to have a block list to block certain devices from checking our block list because Android. Yay. So that's just like a whirlwind sampling of some of the issues that we found while we were bringing up Android. And the important part to note here is that we are very much not done. As I mentioned before, we're still going to be working on additional OS versions and GPUs. We want to get this out to as many people as possible. And also, this is just like the first pass at things. We haven't actually done anything in the way of optimizing for mobile platforms specifically within Dawn. Now we expect that most mobile specific optimizations are probably going to happen at an app level. You have the knowledge about what's going on that we don't, but there's probably still things that we could just be doing better. And we would love your help finding those kind of things. We have exposed some extensions that are aimed at making mobile better, stuff like FP16, but there's work to do. And then we expect that there's going to be probably a decade or more of ongoing maintenance, just like we've done with WebGL, because this is part of the web. And we're making a contract with our users that this is something that they can depend on. It's going to be ubiquitous eventually, and it's not going to just disappear from under their feet. So it's something of a never-ending journey, but we're proud to do it to make sure that all you lovely people can take advantage of this great technology. And that is my talk.
All right. Thank you to Brandon, the entire WebGPU team, both at Google and at other vendors for just creating an awesome ecosystem. I'm so excited to be part of it. So I'd like to ask all the presenters to please come up for Q&A. The bar closes at 8:55, so if you wanted to get a drink, go now and come back in, and we'll stand up here as long as people have questions, and otherwise we can just mingle outside and you can ask more questions out there. But if you want them recorded for posterity, now's the time to ask. So please, presenters, come up, and lovely people, please ask questions if you have any. And if nobody has a question that you want in the recording, we don't have to keep going. But please, ask questions. Please.
So for WebGPU compatibility mode, is there going to be a flag I can turn on in my app to say, I want to test compatibility mode on desktop?
So the question, I have to repeat the questions. The question is there going to be a flag to turn on compatibility mode so you can test on desktop? Yes. And would anybody else like to answer this question, or shall I do it? Okay. So basically, if you look at the compatibility mode proposal, which will hopefully be merged into the spec soon, yeah, there's just a new flag that you pass this into request adapter, and that puts it into compatibility mode. So on implementations that support compatibility mode, they will do the validation. Now, unfortunately, the backend will probably still have the full functionality, so you might want to test on like an old Android phone or an old Chrome OS device.
Cool, thank you.
Yep. More questions. Questions for Rive. Questions for Unity. Please.
For Rive, does it block the main JS thread when it does its WebGL calls, or does it do stuff in the service worker so that the main JS thread doesn't get blocked from doing that stuff?
It's not in a service work. Oh, sorry. The question is if any of the calls that are made for Rive's rendering are in a service worker or in a web worker.
Does it block the main JS thread when it's doing WebGL?
It does, but it's very lightweight. What we do on the CPU side is really, really minor. Most of the work happens in the shaders. So if we find that that's a problem, like you saw with the text demo, I think we can explore things like that. But currently, yes, it's all on the main JS thread.
Are the compute shaders dynamically created so that you have to re-upload them and then therefore block the thread, or do they stay pretty static?
They're pretty static. We figure them out kind of at initialization time, what we need, and we compile the right ones. Do you want to expand on that? Sorry, I should have asked the question again.
Yeah, the question is if the shaders are static compute shaders. There's one compute shader, which is actually a render shader drawing to a data texture that behaves like a compute sort of shader. And that's just one type. There's only one of them. As far as drawing goes, we do have a few different shaders based on turning features on and off. And I want to look into the KHR parallel compile, which I've seen as an extension in WebGL. And as of right now, we don't do that.
But you only have to upload them once, so that's it.
Well, okay, so oh yeah, the question is you only have to upload the shaders once. Yes, that being said, based on content, we do turn features on and off. And so if you draw a different artboard, you might have to recompile with different features on and off. In Metal, we have a single shader with all of the features on, and you use that instantly. And then in the background, we compile the more specified one, the more specific one with features on and off. And we can do that with KHR parallel compile. We don't do it yet.
Is pixel local storage compatible in principle with WebXR compatible buffers? Like, you be able to do it on that?
The question is, are pixel local storage buffers compatible with WebXR? I don't know, because I don't know what WebXR is.
Somebody does.
Yeah, well, okay, so I will speak into the microphone. Let me ask, do you use pixel local storage with the default frame buffer?
As of right now, no.
Okay, then the answer to your question is yes, it should be fine. You can use them in parallel.
Yeah, the question is if Rive render would benefit from WebGPU. The answer is I believe so. So we have it on Metal, for an example, and it's a fair amount faster than on Angle. So my belief is that WebGPU will be faster unless it also has the slowdowns that we don't fully understand. I suspect the slowdowns are the Angle shader compiler, but again, not sure. I believe so.
I'm curious, can you explain how to handle font engines? Like, how do you elaborate those? Fonts are crazy, right? There's kerning, there's so many stuff.
Oh, yeah.
How do you just touch upon this?
So the question is how do we basically bring font data into the renderer, into the format? The format, Rive's format is open source. We do rely on HarfBuzz and on SheenBD for text shaping, and so we only use it to get the vector data out, and then we use it also to drive some parameters for example, our editor can let you animate font variable axes. You can animate those on a timeline. We will actually reshape based on those rules, so you can cause line breaking to reflow as you're changing variable axes and the like. And so we have rules around that and how we control those, that engine, but it is fundamentally HarfBuzz, and we then just send the vector data over just the same as we do for all our other vector data.
So obviously we work on vendor tools for the Vulkan layer. We get a sort of steady trickle of questions from developers going, I'm developing on WebGL and Android. How do I connect a profiler when you're running on Chrome? So the Android policy is your app needs to be debuggable. If you're deploying onto the release browser, you can't connect any layers, you can't connect anything. Is there any plan for kind of how we help developers actually create the content on Android, profile and debug?
Right, so I'm going to try to repeat the question to the best of my ability, and you tell me if I'm getting it right. Basically, it is hard to do GPU debugging on Android, especially in the context of a browser where you can't like connect the Vulkan, the debug layers that I was talking about. And so, are we going to have mechanisms that make that easier? Right? Yep. Okay, cool. Yes, debugging on Android is hard. I have not personally found a reliable way to do like shader level debugging or the type of debugging that we're talking about. going through tools like the one that Brendan showed off. I don't have great answers for that. I think a lot of the existing tools are kind of a per GPU thing. We do have the ability to turn the Vulkan debug layers on in with a flag, but I believe that they're disabled in Chrome at the moment because of really silly, like, what's the base level API version that we compile against, and we need to be like one version higher than we are. So the story around that is just not great right now. We don't have a lot of mechanisms to do it. Hopefully we will improve that in the future. Certainly we want to turn the ability to turn the layers on as soon as the API version that we're compiling against allows it.
I'm not sure if there's any overlap between the WebGPU performance testing suite people and the folks who are involved in USD, glTF, and MaterialX sort of specification work, but there is, like, what extent is the concept of a performance testing suite sort of present in all of those other testing futures?
Everybody's running away from the mic.
I walked away. Run away.
I don't know why I volunteered, but I probably will disappoint you. There is no such thing as tests for glTF as for today. Actually, we consider to do this something like this for glTF USD interop, basically to trace the cases around this. And in fact, actually, we developed the tool as for today that we called asset generator. That probably would be like a first step to create a test suite, because the new extension that's coming in actually creates this complexity that we need to start to test it. But yeah, as for today, yeah, we have just like a repo that you can load and test your, and the problem with glTF, we have no runtime. It's a spec, right? And we want help to developers to test it out, but yeah, that's pretty much it.
Sorry, I just want to add one thing really quick. While you're right that there's no test around there in the strictest sense of the word, I will point out that glTF has a pretty nice library of sample models that Khronos publishes that do a decent job of exercising the full scope of the API, and that's really useful for a certain set of people who are using it, especially if you're doing any sort of parsing or rendering. It's not quite the same as a test, though.
So that's one of the requirements, actually, if you develop new extension, you have to provide a test model, but it's a reference test model. Again, it's not the test case. But we want to build the tool to allow us to generate test cases.
So let's talk about MaterialX first. So MaterialX has the spec, and then it has the ability to generate shaders and render them. So there is a test suite that validates every node that is part of the MaterialX library, renders them on OpenGL Metal, open shading language, and does image compare and all that. USD has similar test suites for their things. And Henrik talked about AOUSD, so that's the purpose of that organization or that committee is to create a normative spec for MaterialX and USD so that we can bring it as part of an ISO. So that's the reason we have started this, so that we can use it with glTF. Right? Otherwise, we cannot use MaterialX with glTF. I don't know if that answers you. Yeah.
So I have pretty successfully debugged WebGPU on desktop, on Windows at least, with Pix. I have not successfully gotten it to hook into RenderDoc. There's some history with RenderDoc and browsers that I think might be contributing to that. And Xcode just hates me, so I haven't been able to convince that to do its debugging at all. But I know that other people have been able to. And so you can hook into some of these existing native tools, and they do a pretty good job of surfacing the type of thing that you're looking for. Now, the caveat is that you're making WebGPU calls, and what the debugger is going to surface is DirectX calls, or something like that, if you're using, say, PIX. And that can be a little bit of a frustration because it's not always going to be one-to-one, and there are going to be some fix-ups that we push into there. But yeah, for a more like one-to-one WebGPU-based debugging, I would probably look to more tools in the future like what Brendan was talking about. It's not that it's not possible. A lot of times it's just a real pain to set up. And a lot of it is due to the fact that it's a browser, we don't look like a game, we don't have the same kind of loop. Our rendering is happening in a separate process, it's a sandbox process, all these little things that most applications just don't have to deal with. And in a lot of cases you can work around it, but it's just a pain. I've got a write-up of at least how to connect to PIX on my personal website, which is listed in the slides. So that's a decent place to start. Obviously, that only works for people who are developing in Windows, but I'd like to expand it more. If anybody else has hints on how to use some of the tools out there, then please email us. We'd love to hear them, publish them, get the message out there, because it is something that a lot of people want and need and is not always the easiest thing to do. Then Patrick, I think you wanted to ask a question?
Oh, thanks, Brent. Yeah, actually I had a question for Ashwin. I love the procedural texture work for glTF. Do you think, is there any overlap with the glTF interactivity work? Like for the node graph? Do you think anything will be common there?
So the question is there any commonality between the interactivity extension and procedural in terms of how it describes the graph? So the concepts are similar, where you're defining nodes and you're connecting them up. We have not looked at reusing that extension model to mimic this, but as we get into the implementation details, we might.
Any questions for the Unity folks? This is GDC after all.
Can I ask one?
Please.
Hi, Brendan. This is for you. I was wondering, and maybe you'll point me just to the forum link that you posted before, but since we use the native plugin system for Unity and we use that to hook into WebGL, does WebGPU is it already accessible to native plugins?
I think so. Oh, the question was already asked in the mic, so I don't need to repeat it. But so the long story of that is if you're using specific GLSL shaders, then I don't have a compiling story for that, right? I only have a compiling story for HLSL to get to Wigzel right now. So if you have GLSL shaders in your native plugin, then I'll add that to my to-do list.
We'll not do that, yeah, for WebGPU.
But as far as a native plugin that for the web platform, and we used to call it the WebGL platform, which is very confusing. So now that we have WebGPU web platform, then you have your C++ code, your JavaScript code, your shaders, all that will pipe in through. And when you have WebGPU as one of your target graphics APIs, then it'll compile it for both WebGL, WebGPU for you, yeah, and then your player will pick the appropriate one.
So what if we want to use a Pixel local storage extension, which requires Wigzel?
We have no direct way of authoring Wigzel right now, which doesn't seem like it. ought to be too hard to add. I haven't done it. I'll add it to my to-do list.
This is one of those things that you're doing because it seems like it's easy.
So, like, for example, if you author a shader in GLSL, which you can do now, and you're targeting GL, which is the only thing you should be targeting if you're doing that, then the translation is just like, here you go, here's your shader. If you author in Wixel and you're targeting WebGPU, then it'll do the same thing. Now, if you include WebGL as one of your target APIs, well, we're not going to reverse compile it back to GLSL, so you're kind of on your own on that.
I see in your shader pipeline you go from HLSL to GLSL to Sphere. Why not use Dixel?
Okay, so the question is, we have a very long compilation process for going from HLSL to GLSL to Sphere V to Wixel. Why don't we use DXC? Is that? Yeah, to go directly from HLSL to Sphere V and then to Wixel. And the answer is it's on my to-do list.
I'm afraid our time in this room is up, so please let's meet in the reception area. Thank you all for coming.